Control system design is an important aspect of modern engineering, finding application in most areas of systems design, be these large industrial installations or smaller but equally complex aerospace systems. In both of these areas, the demands made upon the engineer are such that computer-aided design techniques are a necessary tool for today's engineer. For a number of years, the Control and Instrumentation Group of the Department of Electronic and Electrical Engineering at the University of Salford has been involved in the research and development of innovative computer-aided design tools, these giving the control engineers increasingly sophisticated means by which to realise their designs. Much of this work has so far concentrated upon the algorithmic expression of control systems in terms of computer programs and simulations, and this aspect of control systems computer-aided design has, for many years now, been the main action that's been pursued, with the result that now a number of products actually exist, products such as ACSL, CLAD-P, TSIM, and whilst at Salford we've developed ISIM and ESL. However, these products, good though they are, still have one shortcoming, and that is they're not terribly easy to use, particularly by the novice. He'd prefer a more natural form of expression. Obviously though, this kind of work is going to come after the development of the numerical part, but now it can no longer be ignored, particularly with the advent of affordable graphics workstations. To help us see how the user's interface has developed, let us briefly look at the way these packages have progressed from the genesis of the early digital simulation programs. These early programs used a question-answer form of interaction to specify the nature of the control system to be simulated. Now this is quite cumbersome and often requires a fair degree of background knowledge from the user to be able to competently use it. Hence there is little to connect the design as seen in the head of the engineer and that used to specify it to the program, as computer graphics was little used in the visualization of the design, apart from being used in the presentation of results. More recently, one obvious extension of this type of program was to modify the question-answer session to become a menu-driven system, freeing the user from having to remember a plethora of commands. This can then be augmented with readily accessible and detailed help, and now the novice has a chance. Furthermore, as the capabilities of the equipment improved, so too did the means by which the user could describe the nature of the design to the program. One such method is a form of description used by control engineers called a signal flow graph, or alternatively a more conventional block diagram. Essentially, both can be represented in much the same form. And when this is used to specify a system's topography, the potential becomes apparent. There are, however, other favoured descriptive forms used to describe control systems, such as using a specially designed expressive language to define the algorithms that constitute the simulation of a control system. With these, the engineer specifies the system to be analysed in the form of a program, which is then run to yield the results detailing its performance. Although this form of description is very flexible, it can presume of the user a high degree of computer literacy, so these packages are often used in a form where frequently occurring control system elements are supplied as pre-written modules, with the users assembling these to define their systems. As the requirement to solve a control problem often exists in many other areas of systems design, then the accessibility of the modern and sophisticated design packages should be extended to the entire engineering community. The engineering community require a modular approach to their problems, which is visible to the average user, making available the current design packages that are on the market. Graphical descriptions of a modular and hierarchical nature, in fact, would make such a design technique accessible to nearly all users. In fact, many professional establishments already use precisely defined modular and hierarchical methods of work. This fits in well with the Salford package called ARGOS. So what is ARGOS? The acronym stands for a Real Graphical Operating System, where such a system is expected to maintain a range of graphical structures accessible to the user through an editor, and file these away on disk for future use. The editor, or symbol generator, can be considered in much the same way as a text editor would be in a conventional operating system, in that it allows a single picture or symbol to be edited. Each of these symbols can contain references to other previously defined symbols, linking their functional properties in a graphical form. It is these functional aspects of the database which are most important in terms of the useful application to system specification. Therefore, this part of the user environment is used to run the graphical programs when they are edited. Storage and access is facilitated by a database file maintained in ARGOS, accessible to the user through the symbol menu. The symbol menu acts as a window into this graphics database, from where the user can inspect and rearrange the selected symbols. Again, as with a conventional operating system, each symbol is treated as a single entity as a file would be. Furthermore, a small part of the whole database is available within the symbol generation environment, where it can be treated as a subdirectory of the whole database, allowing the user to use this to acquire any accessible symbol by direct selection for use by the editor. As can be seen, a command is performed by simply pointing at the command to specify the action and then pointing at the item upon which it is to have effect. In a number of cases, there is an implicit action to be taken upon selecting an item, all of which gives the user a working environment within which it is easy to learn. However, this is not all that is required to support the application of a user's program in such an operating system like environment. Additionally, the system has to detect errors within the database, these then being trapped and reported, and hence preventing the database from being corrupted, or worse, causing ARGOS to crash. Furthermore, to add additional flexibility to the program, facilities are included to enable the user's specification for these messages to be incorporated, whilst other system-specific parameters can be modified by senior users of ARGOS, all of which is intended to enhance the user-friendliness of the package. The interpretation of a graphical structure with the object of driving a control simulation and design package can be approached in two main ways, either by direct interpretation of the formatted data or some form of source code generation. Initially, the direct interpretation method was used upon a time-response simulation program developed at Salford, where that program used a model of control system described by a network of interconnected single-input, single-output modules, being largely based upon the signal flow graph methods. In its original form, data was supplied by a question-answer session specifying the topography and modular data. Now within ARGOS, this same program is supplied data embedded within the graphical descriptions for the modules, hidden from the user so as not to confuse, whilst the topographical information is extracted directly from the graphical structure. Hence, as all the information relates in a graphical manner, then the graphical description of a system can be interrogated by the user, and as the interpretation is running within ARGOS, then the resultant time responses can be related back to the relevant points within the structure. This type of program specification is both simple and very obvious, demanding little from the computing skills of the engineer, who can instead concentrate upon the design problem. The second interpreter under development produces source code, as this method is much more flexible. It's more flexible because many of the modern control system simulation and analysis packages require the design to be written in a special language. From this point of view, one possible method is to break the data definition to two levels. The lowest of these will be used to generate the actual lines of source code from a structure with some well-defined semantic form and graphical syntax, such as the form offered by that defined in British Standards 6224, a specification for design structure diagrams for use in program design. Now, each of these programming elements may then be used together to form discrete modules of code, such as is required to define a typical control module. It is these modules that the application's user would normally have access to during the specification of control systems problems. For example, a logical AND gate will be specified as follows. A specification of the code in a procedural form using the design structure symbols is generated by some senior applications engineer. This is then defined as being within the symbol which describes itself to the user as an AND gate. But from the user's point of view, the code structure is invisible and only the AND gate symbol is visible. with the result that these control modules are now available for use in the composition of a system to be simulated by a control engineer. When such a description is now passed to the interpreter, source code describing the system is produced in the relevant control simulation language, dependent upon the data defined within the database of ARGOS. This source code is in turn passed through the necessary pre-processing and compilation phases before being executed. All this can be performed in parallel with the operation of ARGOS, with all processes communicating such that the results can be presented back to ARGOS and displayed. So ARGOS is one possible way of improving the interface to the sophisticated design and analysis packages currently available and making them accessible to the wider engineering community. Also, as the range of graphical devices on the market increases, so too does the need to implement a package such as this on the variety of hardware environments now available. So not only do we have ARGOS running upon a VAX computer, driving a Tectonics display terminal, but we also have it under development on a Sun workstation, and similarly under development on an Apollo workstation. Currently, this work is being supported by an industrial partner and the Science and Engineering Research Council, showing the level of evident interest that exists where the emphasis is on user-friendliness and flexibility. Similarly, other work is also being supported by the Science and Engineering Research Council within the wider academic community looking at this same target. So soon perhaps, analysis tools that are currently available will find wider acceptance within the engineering community, in particular with implementations upon the new, cheaper, self-contained systems now available.